Okay, we should be live now. So let's begin. So we are now at lecture 15. And this and the next lecture will basically be the two lectures where we will finish bivariate polynomial factorization. And once we do bivariate polynomial factorization, you will see that everything will basically be reduction to one less variable. It will be something like, we'll reduce many of the tasks that we want to do for bivariate polynomials to similar tasks involving univariate polynomials and somehow make use of that. And just that this machinery will let you now do the same thing for trivariate polynomials, four-variate polynomials, etc. Because it will all eventually boil down to, if you know how to handle k variables, here is how you handle k plus 1 variables. That's typically how all of these algorithms will go. And as I mentioned, there are a bunch of tools that we need to pick up. So one very important tool is this notion of resultants, which will be a good chunk of today's lecture. And then we'll deal with Hensel lifting once again, but depends on how much time we have left today. If required, it will get pushed to the next lecture. But there was also something that we missed from, we didn't cover in the previous lecture, which is that we used the Chinese remainder theorem, but we didn't prove it. So today what we'll first do is we'll finish off that proof. And once we prove that, we would have now completed our discussion on factorization of univariate polynomials over finite fields. And if you recall, we'll quickly go over it anyway. We saw the Cantor-Zassenhaus algorithm, which gave a randomized algorithm to do factorization of univariate polynomials over a finite field. And internally, it used the Chinese remainder theorem as a part of its analysis. Though, you didn't have to do any computation involving CRT, but nevertheless, it was very useful in analysis because you could somehow argue that, you find these zero divisors with high probability and stuff like that. Okay, so that was the rough idea last time. So today, primarily, we are going to try and focus on resultants and get across that one main idea. And depending on how much time we have left, we will revisit Hensel lifting. And this time in the context of factorization. Previously, we saw this Hensel lifting, this iterative methods, when we were doing polynomial division or something, because we wanted to invert a polynomial. So there was some lifting process that happened. We'll revisit that again in this context, and it's something that works in more generality. It's a pretty cool sort of technique to have in mind. And in fact, in your problem set, the second problem set, there is also a question involving not Hensel lifting, but Newton iteration. In my opinion, they're both very similar in flavor, of finding square roots, as opposed to finding inverses or finding factorization, but they're all of very, very similar nature. Okay, good. So let's proceed with just a brief recap so that everybody is on the same page. So we saw the Cantor-Zassenhaus algorithm, and this was roughly what the algorithm was, but we first did some pre-processing initially, which is we did this thing of distinct degree factorization, removing repeated factors, etc., so that you're now in a nice situation. And the nice situation is that I'm just going to assume that f is a monic polynomial, which means the leading coefficient, the coefficient of the highest degree term in x, is just 1. There are no repeated factors. And you're also told that all the irreducible factors are all of the same degree. It's some degree k. Okay, and you also know what this k is. These are all things that this is a situation that you end up with after you do distinct degree factorization. Okay, so this is what you would be. And what was the algorithm? The algorithm was sort of, in hindsight, very simple, which is you just pick a random polynomial of smaller degree. Okay, let's call that h. And step 2 is basically like, if you just got unbelievably lucky. Like if you just try taking the GCD of h with f, and if you get a non-trivial GCD, well, fantastic. You've already found a non-trivial factor, so you just return that factor. Otherwise, somehow you look at the slightly different polynomial, which is h bar q bar k minus 1 by 2 plus 1 mod f. Sorry, comma f. You look at the GCD of that. And we somehow argued based on Chinese remainder theorem that this is a polynomial that will almost surely have, with high probability, have some non-trivial factor with f. And how did we argue this? We basically said, if I look at the Chinese remainder representation of this polynomial, then I mean, like roughly half of them will have zeros and half of them will be 2 or something. If I didn't add this +1, it would have been half of them is like 1 and half of them is -1. So adding a +1 will make half of them equal to 0 and half of them equal to 2. So very likely you're going to get some GCD. The only extra thing is that this is a super large degree polynomial. So you need to do this GCD computation using that repeated squaring. Okay, and that's it. So this will succeed with probability at least a half. Like if you know that f has at least 2 different factors. So therefore, well, if you didn't succeed once, well, keep trying again until you succeed. Depending on what your accuracy is, how much error you're willing to tolerate, you try it a few times. Okay, so this is what the polynomial factorization algorithm of Cantor and Zassenhaus is. Yeah, and we'll just from this point onwards, we'll be happy with just randomized algorithms. But it's a good thing to keep in mind that making this a deterministic algorithm is a major open problem. So, I mean, we still don't know how to do that. There are special cases in which we know how to do deterministic polynomial factorization. But the general setting of trying to do polynomial factorization in deterministic n, log q time, this is still open. By the way, I might keep switching between n and d, but what I mean here is that they are like the degree of the polynomial involved.
So whatever you're saying that the open is still open is for all kind of finite fields or few finite fields?
No. So we know how to do this when the finite field is of small characteristic but large size. So that is something called Berlicam's algorithm. Like for example, if your field looks like f2 to the 1000. So in such situations, we do know how to do deterministic polynomial factorization. But the canonical hard example is when this Q itself is a prime and this prime is huge. And then it feels like, the best we are able to do currently is a randomized algorithm. We don't know how to construct a deterministic algorithm.
Means can't we do one thing that we can embed fields? Suppose we have a big field F, finite field, but we are embedding in itself some finite fields F1, F2 dot like a chain, so that it approximate the F. Eventually.
No, but like for example, if your field is basically FP where P is a huge prime, I mean, there's no embedding that we can do, right?
Okay.
Yeah. So yeah. So so this is I don't know. I don't know concrete evidences for whether people believe that this is we should be able to do it in randomized, deterministic polytime or not. I mean, since I work in complexity mostly, I tend to believe that BPP and P are the same. So in many situations, you can eliminate the need for randomness. I believe this is one such situation, especially because the situation is very similar to a lot of other questions where we knew how to solve this for a variety of special cases, and then it just took some new idea to do this. But I have not worked on this problem, so I don't know much more about this. Yeah. Okay, so what we are first going to do is we are going to prove the Chinese remainder theorem for ideals. And then we'll proceed towards this marathon for bivariate polynomial factorization. Okay, so before we go to Chinese remainder theorem, we need a bunch of definitions. This is something that I mentioned last time, which is this notion of co-prime ideals. Okay, sometimes these are also called co-maximal ideals. Okay, which is to just mean the following. So two ideals I1 and I2 are said to be co-prime or co-maximal if there are elements in I1 and I2, let's call that small I1 and small I2, such that they sum up to 1. Okay. Another way of saying this, this is probably going to tell you why it is called co-maximal, is that if you look at the smallest ideal that contains both I1 and I2, in particular, it must contain 1 because the definition said that one of these elements is 1. But if an ideal contains 1, notice it must contain everything. Because if A is in the ideal, then for any polynomial f times A must also be in this ideal. So this will basically force this ideal to be the entire. So in that sense, it is co-maximal, in the sense that the smallest ideal that contains both of them is basically everything. Okay.
So this is generalizing this, that if A and B are co-prime, then A
Exactly.
plus B is
Right.
plus 1.
So for example, something like this. So we know 12 and 35 are co-prime integers. Okay. But you can rephrase it in the context of ideals and think of 12 and 35 as generating its own ideals inside the set of integers. And you observe that it is actually co-prime or co-maximal just because of the fact that if you run the extended Euclid algorithm, you will find some multiple of 12 plus some multiple of 35 equal to 1 because their GCD is equal to 1. So that satisfies this, and therefore they form co-prime ideals. So it's just a in some sense the right generalization from the context of Chinese remainder theorem. Let me put it that way. Okay, so this is what a co-prime ideal is. And I also would need one other example, which is this notion of what is called a product of an ideal. I mean, it's the most natural thing you think of. Basically, take all possible products and look at the smallest ideal generated. Okay, so let's maybe take a couple of examples. What will be the product of the ideal generated by X and the ideal generated by Y?
I forgot. There is also another similar definition, that product of the sum of all finite sums, right?
Sorry?
Summation is I1, I2 is equals to summation j equals to 1 to k, ik, I1, I2, like that.
Sorry, you mean this? So where j is going from 1 to whatever.
Yeah, k is any integer.
And I1 belongs to the first ideal and this belongs to the second ideal.
All linear combination of the finite products.
Yeah, but that's the same thing as this taking the ideal generated by them. I'm just saying these are your generators. Okay, and now you are allowed to take anything that you are forced to take. Basically, look at the smallest set of things that you are forced to take. It's the same thing. Yeah. Okay. So now let's look at what is this product going to be. So this is basically the product of all, I mean, these are all polynomials that are divisible by X. These are all polynomials that are divisible by Y. And you can see that these are basically all polynomials that are going to be divisible by X1. So there's nothing fancy that's going on here. So here is one other example, one where one needs to be a little careful. So what can we say about this? What is the product of the ideal generated by X and Y and the ideal generated by X and Y?
Y square.
Sorry?
Ideal generated by x square and y square.
Not quite. So for example, you have to add the generator XY also.
For 2xy terms.
Sorry?
For the xy terms, 2xy, something like that.
Yeah. So it's not. So that's the reason I had sort of mentioned this is just it's not just x squared and y squared, because xy is also something in this product. Because x belongs in this ideal and y belongs to this ideal. So your ideal is forced to include xy also. If you had not taken the xy and you had just taken x squared and y squared, there is no way for you to generate xy.
Yes.
Right. So one needs to be a little careful. So when someone says x comma y squared, it's not saying that it is x squared and y squared. I mean, there may be these cross terms that you might have to consider. That's the only thing I wanted to point out at this point. Okay, good. So here is a simple observation, which is that whenever I1 and I2 are co-maximal, okay, then it turns out that the product of the ideal is the same thing as the intersection. There's no real difference between them. So as you can see in the first example, notice these are the set of polynomials that are divisible by xy. I could have instead written it as these are the polynomials that are divisible by x and also by y. I would have gotten the same thing, but I can't do that here. I mean, if I call this as an ideal I intersection I is equal to I, but that's not the same thing as, I squared. So it's not always the case that the product is equal to the intersection, but when they are co-maximal or co-prime, then they turn out to be the same. And the proof is actually quite simple. Okay, so which is the easy direction? Which direction is clear?
Oh, this is an if and only.
I1.
Is it an if and only if? That's a good question. I don't think so, but I don't have a counterexample off the top of my head.
What is the question?
So, it means
So,
there's only one direction.
Yeah, the question was, is this an if and only if? Because basically speaking, that co-maximality is something to do with where their behavior in the ambient space. Whereas this statement could be true for very small ideals inside a large ring. I mean, it might be the case that I1 and I2 together are nowhere close to generating all of R, but maybe they still satisfy this equation. I mean, I don't have a concrete example off the top of my head. This is the reason why I believe it's not an if and only if. But yeah. Okay. So let's try. Okay, let's prove this direction first. Which is, I want to show that I1, I2 is a subset of I1 intersect I2.
If you take 2z and 4z, work with.
Sorry?
If you work with 2z and 4z.
Yeah, but 2z and 4z are not co-maximal.
Yes, but they satisfy ideal equation.
No, they don't, right? I mean, like 2z intersection 4z is equal to 4z. But 2z times 4z is 8z.
Yes.
Yeah, so they're not the same. Yeah. Okay, so let's try this containment. So what do I need to show? I need to show that all the generators of I1, I2, if I can show that they belong here, I am done. Because then everything that they generate will also belong to the right hand side. Okay, now let's take an arbitrary generator. Let's look at I1 times I2, where I1 came from this ideal and I2 came from this ideal. Now, can I somehow convince you that this must be present in I1 intersect I2? Okay, why is this present in I1 firstly?
I mean, it's I1 times I2.
Right, so it's I1 times something. So the ideal has the property that I1 times something is an I1. Right, so this is certainly present in I1 because this is like I1 times something. And it's also present in I2 because it's like I2 times something. Okay, so therefore it is present in both I1 and I2, therefore it's present in I1 and I2.
Here we didn't need co-maximality.
We don't, yeah, exactly. We didn't use co-maximality at all. So one containment is true for all ideals. So it's the other containment that somehow we should use co-maximality. Okay. So basically now what do I want to show? I want to let's pick up any arbitrary element of I1 intersect I2. I want to be able to write it in terms of elements of the form something in I times something in I1 times something in I2. Okay, so we need to use co-maximality somewhere. So therefore, let's assume that I1 plus I2 is equal to 1. Okay. Now, can I write this as some alpha times something in I1 plus some beta times something in I2? I want to write A as this. Or okay, this is not quite what I want to do, but so basically, I mean, I don't know how to motivate this. So you basically just take this equation and just multiply by A on both sides. Okay, so this implies that AI1 plus AI2, this is equal to A. Okay.
Oh, so
I claim that both these elements are present in I1 and I2. Why is that? Here is an element in I1 times an element in I2 because I chose A from the intersection. And this is an element of I1 times an element of I2 that's also present in I1 I2. So therefore, this is an element of I1 I2. So this immediately puts it in I1 I2. Okay, I hope this was okay. So this is basically just a simple proof as to why coprime ideals behave nicely when it comes to products or intersections. Okay, great. Okay, now that we have this, we can now state the Chinese remainder theorem, which we stated last time. I am stating it for just a pair of ideals. I mean, this is pure laziness. But basically, there's nothing different that happens when you have more than two ideals. Okay. So in that case, you will want to say that the ideals are pairwise co-maximal. Like every pair of them is co-maximal, etc. And the Chinese remainder theorem basically says that R quotiented with the product splits nicely as a product of R quotient the single things. And since they are co-maximal, you could write this as R quotiented with I1 intersect I2. Okay. Now, I mean, hopefully the statement is something that is very believable because this is something that you would have seen over integers. So it's just saying, if I have a product of co-prime numbers, if I have a bunch of pairwise co-prime numbers, and I'm interested in whatever integers modulo their product, I might as well consider just their separate residues and work with them. And there is no loss in information. That's basically what the Chinese remainder theorem says. And this is something that you have seen for integers, and we are just going to write it for ideals in general. Because we ended up using something very similar for the Cantor-Zassenhaus algorithm, where these I1, I2, etc. were based on the factors that you got, the factorization that you had got. Okay, so what do I want to do? I want to find an isomorphism from the left-hand side to the right-hand side. Okay, and I don't know how many of you have seen problem set 2, which is that whenever you encounter situations of this sort, where you're trying to show that you're trying to construct an isomorphism that looks like R quotient something being isomorphic to something else, the thing to use is what is called the first isomorphism theorem. So let me just say that in problem set 2, you would have seen the following. Whenever you have a homomorphism from two rings, I mean, it doesn't have to be rings, it could be anything, it could be groups, it could be vector spaces, whatever. Okay, so from R to S, then you immediately get that R quotiented with the kernel of phi. This is isomorphic to the image of phi. So notice the image of phi is going to be some whatever subring or something on the right hand side. And this is something that is present on the left hand side once you take the quotient, and basically says that R quotiented by the kernel is isomorphic to the image. Okay, this is something that you will have an opportunity to prove in problem set 2. And this is a very general statement. I mean, you probably have seen this for vector spaces, for instance. This is a different way of stating the rank nullity theorem. Okay, and the similar statement is true for groups. So it's one of these fundamental things. It's called the first isomorphism theorem. Okay, so therefore we are going to use this. I'm just going to assume that, I mean, this fact is true. You will prove it in your problem set. So now what do we want to do? I want to show an isomorphism from R quotient I1, I2 to something. So here is what we are going to do. So we are going to find some map from R to R quotient I1 cross R quotient I2. And we'll try to prove the following facts. That phi is a homomorphism. We'll construct a phi such that it happens to be a homomorphism, and such that the kernel is exactly equal to what we want. This is equal to I1, I2, which we have just seen that this is equal to I1 intersect I2. And that phi is surjective. I mean, that is what I mean is the image of phi is equal to all of the right hand side. So that will immediately tell us that R quotiented by the kernel is isomorphic to this from the first isomorphism theorem. So far, so good. Okay. Okay. And normally, in many of these situations, there's almost only one map that works. I mean, there is a natural map and you just try it out and it just works. One just needs to carefully, sorry?
Like the representative process.
Exactly. So you just take the following map which is you take an element X, and what do you map it to? Well, the only thing that you know you can, which is map it to X mod I1 and X mod I2. Right? I mean, like it's one of these things where I don't know what else to even suggest here. I mean, so this is the thing that you do. And I mean, okay, that this is a homomorphism is usually trivial to check. You just need to verify that your usual properties work, but we already have seen that modulo operation is something that whether you multiply and then take modulo or take modulo and then multiply, it doesn't make much of a difference. So therefore, I mean, this is something that you get for free. So now let's ask the second question. What's the kernel? So when will an X get mapped to 0 on the right hand side? So it means it must get mapped to 0, 0 here. Right? And what does it mean for the first representative to be 0?
That it's in I1.
So that it is in I1. So if it is already in I1, then the representative will be 0. Okay. So an element in the kernel automatically implies that X must be an element of I1 and of I2, and which we have just seen this is equal to I1, I2. Okay. So the kernel is fine. And usually the tricky part is why is phi surjective? Why is it the case that you pick up an arbitrary pair of cosets? I am supposed to find an X such that it maps to that. So I somehow need to convince you that, I actually cover everything. Okay. Now, I don't know. I mean, I'm hoping that you have seen the proof of the Chinese remainder theorem in other contexts. So there is a certain way in which you often show that these things are surjective by actually trying to find images of certain special elements, or rather pre-images of certain special elements, in a way that it gives you pre-images for everything else. So in particular, what you would want is, I want to know what is this element alpha that ends up getting mapped to 1, 0, and what is the element beta that ends up getting mapped to 0, 1. Okay, because then if you want to know, if you want to know what get maps to X, Y, okay, you just notice that this is going to be X times alpha plus Y times beta. So this is a usual trick that you do. I mean, like you might have seen in the standard Chinese remainder theorem, something that is divisible by all the other numbers, but leaves residue 1 when divided by this guy. You would have tried to come up with some version of that. Okay. Again, once again, we have not used co-maximality yet. Right? I mean, we know I1 and I2 are co-maximal. So far, we have not, okay, we have used it in these things. But let's, what do we know? I mean, we know that I1 plus I2, this is equal to 1. Okay. And so let's ask ourselves, is I1 or I2, are they good candidates for alpha and beta? Okay. What will the representative for I1 be? Okay. So notice that phi of I1, I need to basically say which coset of capital I1 do you belong to, which coset of capital I2 do you belong to. What is I1 mod capital I1? Well, it's an element of that coset. So that's actually equal to 0. Okay. What is the coset representative of I2? What is I1 mod capital I2? Okay. Notice that if I just take this equation and go mod capital I2, this just becomes 0. So I end up getting 1 here. So in fact, I1 is going to play the role of beta and I2 is going to play the role of alpha. Okay. So that more or less completes the proof. And that's it. So this is the standard Chinese remainder theorem, which is you're just going to make use of the first isomorphism theorem and set up a homomorphism that has the right kernel and it happens to be surjective. So hopefully this is something that seems reminiscent to stuff that you have seen for integers and stuff. And it's more or less the same proof, but written in sufficient generality so that you can apply it to in various other contexts. Okay, great. So if there are no further questions, we are going to start moving towards bivariate factorization. And as I mentioned something, I mean, there's going to be a bunch of things that we need to pick up on the way. So what I'm going to do is I'm going to start off with certain simple tasks so that I can use these simple tasks to introduce one tool to you. And in the next lecture, we'll put them all together. Okay, it's a pretty awesome algorithm due to Mansur Gattan and Eric Kathofen, which we'll see in entirety in the next lecture. But today we'll just pick up tools necessary for it. But I'm going to start off with the following question. This is something that we take for granted in the univariate setting, and it already becomes non-trivial in the bivariate setting. Okay, this is just the simple task of I give you two polynomials. Can you find its GCD? Okay, so I mean, as you can imagine, this will also go through a very similar process. We'll first get rid of these repeated factors and nonsense like that. And whenever we want to do that, it feels like we want to do some GCD with a derivative or something. But how do we even compute their GCD? Okay, so this already becomes a little clear, a little unclear, because I mean, how did we do this for univariate polynomials? We applied the Euclidean division algorithm. Now, the division algorithm, when you're dealing with bivariates, is already something weird, right? Because there are these, I don't know how to really motivate it, in the sense that you'll have to divide by polynomials and stuff like that. You need to worry about whether or not those divisions make sense, and yeah, it's just a slightly tricky thing to work out. So one needs to be a bit more careful about it. So here is one idea that we can try, which is, can we pretend that these are polys in, I'm going to write down some symbol. Okay, and let me explain what this is. This is this world of all possible fractions involving a polynomial in y divided by another polynomial in y. Okay, so these are called the rational functions in y. In some sense, basically because I know what to do when I'm dealing with polynomials in one variable over a field. So I'm somehow trying to pretend to work inside a field and hope that everything just works out as is. Okay, none of this is justified, but this is just one idea that we can have. I mean, in the course of the division algorithm, we'll have to divide by certain terms. I may not know how to divide by polynomials in general. So let's just introduce denominators, like, artificially. Okay, so this is what we have. And this leads to another annoying problem, which is, does this change reducibility? Okay, by which what I mean is the following. One needs to be usually very careful when you suddenly change your underlying field to something else, because you could have a polynomial that looks like x squared plus 1, but instead of working over the reals, had you worked over the complex number, suddenly things factorize a lot more, right? So one of the things we need to convince ourselves that, okay, actually these were honest to God polynomials. I am just pretending as if there are denominators in y. But does that change the notion of what the GCD is? Like, if the answer itself is changing, then this is like a weird, I mean, it's something that I can't reconcile. Okay. So it turns out, fortunately, that the answer does not. And this is called Gauss's lemma. And I'm going to state Gauss's lemma for this specific example where you're dealing with integer polynomials, where I have just replaced f of y with the set of integers, And this, whatever, the set of denominators introduced is basically our rational numbers. Okay, just because I just think it's just easier to tell you what the proof of this is, or to convince you that something like this is true, and this just works for more generality. But this is the first thing I want to tell you. It's called Gauss's lemma, and it's super useful, which says the following. Suppose I'll use capital lettered polynomials to mean that all the coefficients are actually integers. Okay. And suppose you know that I have an integer valued polynomial that happens to be reducible over Q. By that, what I mean is that I am able to write capital F of x as g of x times h of x, where g and h possibly could use rational numbers in its expressions. That is, their product only involves integer coefficients, but somehow, g and h internally uses some weird denominators. Okay, I want to claim if there is an expression of this sort. Okay, then I want to claim there is actually an expression of this sort also. Okay, so that's what the Gauss's lemma says. In the sense, if you're dealing with an integer polynomial, there's no reason for you to expect that the factors will somehow involve fractions. That will not happen. Okay, is the statement of the lemma clear? Okay, so this is what we are going to prove. This will basically allow us to freely move from the world of integers to the world of rational numbers, because factorization does not change. I mean, it stays the same. So we can sort of work with rational numbers whenever necessary. Okay, so let's see the proof of this. So let's start off with an expression that looks like this. And again, as I said, these are both polynomials in Q of x. I mean, they potentially use rational numbers in their expression. Okay, so what we'll do is, if I give you a polynomial that involves rational numbers and I ask you to convert it to an integer polynomial, what would you do? You'll basically take some LCM involving all its denominators and pull out these common factors and so on, right? So we can always write this as something of the form m over n times g of x times h of x. By which what I mean is I've just pulled out all the denominators, taken their LCM. So this entire thing became g of x by something. This became h of x by something. And I've just collected the common factors in the denominators and the numerators on the outside. Is that okay so far? Okay, good. So here is what we are going to assume with our laws of generality, that there are no common factors between all coefficients of g of x. That is, if there is an integer that is common throughout all the coefficients of g of x, I will pull that out inside this m. Similarly, I'm assuming that h does not have anything that's common across all the coefficients of h of x. There are no common factors like that. There's no obvious way to pull out more integers. Okay, so what does this mean?
Cases, right?
Sorry?
If m and n are co-prime and if m and n are not co-prime.
Yeah, so I basically want to somehow argue that m and n are the same. Okay, in fact, I want to basically argue that n must divide m. So that is, there is actually nothing here. I mean, it's a proper integer factorization. And so that's what I'm trying to argue at this point. Okay, now why is that true? So let's just do the following. Let's just do, this can be written as n times capital F of x equals m times g of x into h of x. Okay, now I somehow want to argue. Now notice that on the left hand side, capital F of x only had integer coefficients. Therefore, all the coefficients of capital F of x are all divisible by n right now. I mean, in the left hand side currently, because they've been multiplied by n. So every coefficient there is actually divisible by n. Okay. I want to claim that if I look at this polynomial, forget the m outside. If I just look at g of x times h of x, I want to claim that there is no integer, I mean non-trivial integer, that divides all the coefficients in the product polynomial g of x h of x. Okay, so let's just, this is often called a name. So the content of a certain polynomial g, this is equal to GCD of all coefficients. That is, whatever is the common factor that is present across all the coefficients. Okay, and I'm trying to show that the content of g of x h of x is equal to 1. But on the other hand, the content of the left-hand side is at least n. I mean, I don't know what common factor f already had inside itself, but it's at least n, and I want to argue that therefore n must divide n. Is this okay so far? Okay, so I'm going to do a slightly cheating proof here to this thing. So let's just say I'm interested in g of 0 plus g of 1x, blah, 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 blah. I don't know what this is. So this is going to be some g of d x power b. That's what g looks like, times h of 0 plus h of 1x plus, this is probably h of d prime x power b prime. Okay, that's what this product looks like. Okay, now I want to know, okay, what are we given? We know that GCD of G0, G1, blah, 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 till GD, this is equal to 1, and it's also equal to the GCD of H0, blah, blah, till HD prime. That is, there is no common factor across these coefficients. Okay, but their products, I mean, who knows? Now they could have common factors. We are somehow trying to argue that the product cannot have common factors. Okay, so the claim I want to make is that for any prime p, okay, there is some coefficient of gh that is not divisible by p. So this will basically tell you that the content on this product is equal to 1. Okay, and can someone say how you would go about proving it? Why is that true? Okay, so I know for a fact that p doesn't divide all of these coefficients, because if it did, then this GCD will not be 1, it will be at least p. Right? Let's for the moment assume that p does not divide GD. And suppose p doesn't divide HD prime also. Okay, like if we got lucky such that the highest degree terms of those two polynomials were not divisible by p, then when I take their product, the coefficient of x power d plus d prime will basically be the product of these two things, which will now not be divisible by p. So in that case, we are done. Right? If it so happens that the highest term here and the highest term here were not divisible by p, then we look at the corresponding coefficient and we will be done. Okay. Now what's the next step? Suppose the last but one term was not divisible by p here, and the last but one term was not divisible by p here. What would you do then? Okay, so here is a quick proof. Let GI be the highest coefficient not divisible by p, and similarly let Hj be the highest coefficient not divisible by p. Okay, then
Okay, the x to the I plus j.
right, exactly. Look at x to the I plus j. Okay, one contribution is going to be gi times hj. Every other contribution will be some gi times some other, I mean, one of these g's and times one of these h's. But one of them have to be larger than I or larger than j, right? I mean, because they have to sum up to I plus j. And I know all of them are divisible by p. Okay, so this one term is going to be not divisible by p. So therefore, you now get that this particular coefficient is also not divisible. Okay, so this basically tells you that the common factor across the product gx hx is nothing. There is no content there. Okay, but on the other hand, the left hand side has a content of at least n. So it better be the case that this n divides this n. Okay, and well, if n divides n, you just cancel off and you have an integer product. That's it. This is the proof of Gauss's lemma. It's a fairly simple proof, but it's super powerful. I mean, it's just some, like you're just chasing coefficients and somehow convincing yourself that this ought to work. And okay, so it basically tells you that if you're dealing with integer polynomials, reducibility over integers versus reducibility over rationals, there's no difference here. I mean, the only way you can have a polynomial as a product of two rational polynomials is basically one of the polynomials looks like g of x by 1,000 and the other polynomial looks like 1,000 g of h of x. Like I'm artificially introducing denominators, whereas, I mean, morally, there's no reason for me to introduce denominators. Okay, so in general, this is how what is it called? Gauss's lemma is often used, which is whenever you're dealing with a unique factorization domain, this R being some arbitrary unique factorization domain, you might as well work with the fraction field of R. By that, what you mean is you look at all possible like formal like fractions, alpha by beta, where beta is a non-zero number, and you add and multiply things like they are proper fractions. I mean, this usual way. And saying that something is divisible in one world is the same thing as something is divisible in the other. So nothing really changes. Okay, so here is just a concrete example as to what might happen. So for example, suppose you have a polynomial, some bivariate polynomial, which actually splits into factors of the form something that only involves x, something that only involves y, and something that involves both x and y. Okay, now I can also think of this as an element of whatever this thing, where I am allowed to use denominators involving x's in some sense. So then what is the factorization of f of x comma y going to be? The only difference is that this in my world is a constant. No, because it's something that only involves the x's and I'm allowed to take arbitrary denominators here. So I'm going to think of this as some constant alpha, where alpha is basically equal to same g of x, but the other two terms are unchanged. Okay, so this is usually all that can happen when you go from one world to the other. Okay, so far so good. I mean, like this is just called Gauss's lemma. It's something to keep at the back of your head so that you always move to the field of fractions whenever you feel like you want to. Okay, good. Now I want to introduce the next thing, which is called the resultant. Okay, it's an incredibly powerful idea, and this is what will be used to come up with our GCD algorithm. Okay, so again, rather than dealing with bivariates, I'm going to deal with univariates first, so that we get a sense of what the resultants are, and then I'm going to tell you what you do for other setups. Okay, so here is what the setup is. I have two polynomials g and h, which are univariate polynomials over some field. And let's assume that the degree of g is some d1 and the degree of h is some d2. Okay, Now, what I want to do is I want to consider the following map that takes a pair of polynomials a and b and returns the polynomial ag plus bh. Okay. But I want to think of it as, what does it mean to say that this is a polynomial? Well, I'm only interested in polynomials of degree smaller than the degree of h. So that will end up having d2 coefficients, right? This a will have d2 coefficients because the degree is 1 smaller than h. There's a constant term plus everything up till d2 minus 1. Okay. Similarly, b, so just to this thing where I'm thinking of the degree of a is strictly smaller than the degree of h, and the degree of b is strictly smaller than the degree of g. Okay. So therefore, how many coefficients does a end up having? A ends up having whatever d2 coefficients at most, and b ends up having d1 coefficients. So it takes d1 coefficients, d2 coefficients here and d1 coefficients here and spits out some polynomial. Okay. So one way to think about this is that it takes some vector of length d2, another vector of length d1, and spits out one vector of length d1 plus d2. Okay. And I'm just going to, rather than think of them as two separate blocks of vectors, I'll just think of them as one long vector of d1 plus d2. The first d2 coordinates belong to a, the second d1 coordinates belong to b, and you do this map. Okay, it's just some operation, but here is the cool part, which is, so firstly, I claim that this map is linear on a and b. Well, naturally, right? Because if I want to know what is the map on a and b and c and d, and if I add these two up, it's the same thing as applying the map on a comma b and applying the map on c comma d and adding. So this is actually a linear map. It's some linear transformation from d1 plus d2 coordinates to d1 plus d2 coordinates.
Sorry to interrupt.
Sorry, yeah, go ahead.
Degree of ag plus bh is maximum of degree of g comma degree of h, right?
No. So a has degree at most degree of h minus 1. And then I'm multiplying with a g.
A is a field member, not a...
No. A is not a field member. A is a polynomial of degree at most degree of h.
Okay.
Right? So I'm thinking of both a and b. I mean, a and b as polynomials, but presented to me as a bunch of coefficients. And I'm just taking this stupid map, which is ag plus bh. And it's just that this map reveals a lot about what g and h are. So for instance, this map has a non-trivial kernel if and only if the GCD between g and h is not trivial. Okay, so it's a rather surprising fact. I mean, like, one direction is usually clear. Okay, so can someone tell me, suppose I tell you that GCD of g and h is actually non-trivial. So say GCD of g and h, suppose this was equal to, I don't know, some L of x. Okay, so what does this mean? It means that g of x equals, I don't know, some L of x times some u of x, and h of x is equal to L of x times v of x. Okay, can someone give me an element in the kernel?
ux plus vx.
Sorry?
Minus vx minus ux.
Right. Then minus v of x, comma u of x is in the kernel of t g comma h. Because when I feed this into this map, just notice that you're basically going to cancel off both contributions. Okay, so one direction is therefore clear. Like, if there is something in the kernel, I mean, rather, if the GCD is non-trivial, you can certainly find a kernel element. And notice that v of x's degree is certainly smaller than degree of h. U of x's degree is certainly smaller than degree of g. So therefore all is well. So it's a legitimate point in the kernel. So it's the other direction that is a little non-trivial. Okay. So now what is the other direction? The other direction is I somehow want to say,
sir, actually, I have to leave. Medical section called me urgently.
Sure. Yeah, go ahead.
Sorry for
no,
that.
no problem. Yeah. Okay. So we want to somehow argue that the other direction is also true. Okay. So let's assume that the GCD of G and H, suppose this was equal to 1. I want to somehow argue that there is nothing in the kernel. Okay. Now, so it somehow naturally suggests doing something. Once you know GCD is equal to 1, what would you like to do? You'll basically immediately feel like saying that, oh, there exists A and B such that AG plus BH is equal to 1. Right? The only problem with this is that these A and B do not need to respect the degree conditions that we are putting on the fact that I want A to be degree at most H, B to be degree at most G, etc. But maybe you can somehow enforce that as well. But it's unclear from this, how do I go to argue that there is no element in the kernel? Okay, fine. Maybe there is something that maps it to 1. But there could be a different A prime comma B prime such that A prime G plus B prime H is equal to 0. Somehow, in your gut, hopefully you feel like, that can't happen. How the hell can that be true? It's just that we need to formalize this properly. Okay, so here's what I'm going to do. I'm going to just assume the contrary. Suppose, on the contrary, okay, we just have that sum A prime G plus B prime H is equal to 0, where A prime has smaller degree than H and B prime has smaller degree than G. I want to somehow claim that the only way this is possible is when A prime and B prime are both 0. Okay. So let me first show you why A prime is equal to 0. Okay. So I'm going to take this equation and just multiply it by A throughout. Okay. So this implies that A prime G plus A B prime H, this is also equal to 0 because it's 0 times A, so it's equal to 0. Okay. And what is this equal to? I know that AG equals 1 minus BH. Okay. So I'm going to write this as A prime into 1 minus BH plus A B prime H. This is equal to 0. Okay. So if you just rearrange things, what you end up getting is that you get A prime minus H into, what do you end up getting? H into A B prime minus A prime B. This equals 0. Okay. So in other words, this is like saying that this equals this. Okay. Now I want to look at this equation and say this equation is absurd. Okay. Why is this equation absurd? The left-hand side, what is the degree? The degree is strictly smaller than the degree of H. Okay. The right-hand side, on the other hand, is a multiple of H. So certainly the degree is at least as large as H. Unless, of course, that multiple of H is equal to 0. Okay. So this, if non-zero, this degree is greater than or equal to degree of H. But we know that's not possible. So therefore, the only way that can happen is that basically it better be the case that you're looking at the 0 multiple of H. Okay. And therefore, this will force you to admit that therefore A prime is equal to 0. And you can similarly also say B prime is equal to 0 by doing the same thing. Take this equation, multiply by B throughout, and do the same sort of rearrangement, and you will get the other. Is it okay so far? Like this resultant thing? Okay, great. So therefore, somehow this linear map, which takes a pair of vectors or a pair of polynomials, whichever perspective you are more comfortable thinking of, and returning this other polynomial, somehow it has this magical property that this will have a non-trivial kernel if and only if the GCD between the two polynomials is not trivial. Okay, and because it is a linear map, you should be wondering, what is the matrix representation of this linear map? If I were to write this linear transformation as a matrix, what will that matrix look like? Okay, so that's what we are going to do. What is the matrix representation of this? Okay. So normally when you're trying to figure out what a matrix representation of a linear map is, what you do is like you let it act on your basis vectors and then figure out what are those basis vectors going to be. Like for instance, what is the map T, G, H when I act on the vector 1, 0, 0 and then 0, 0. So this is my A and this is my B. This I want to think of as a polynomial which is a constant 1. And this is the 0 polynomial. So therefore, what should I end up getting? I should be getting 1 times F plus 0 times G, which is equal to F. Oh, sorry. I'd written G and H. Sorry. G and H. So therefore, this is equal to G. Right? So therefore, the first row, for first column is just going to be something like GD1. Okay. Okay. Now let's do the next thing. This is the vector which is 0, 1, 0, 0, 0. What is the polynomial that corresponds to this?
Like X.
It's just X, right? So therefore, this is going to be X times G plus 0 times H, which is X times G. So it's the same thing, except it's now going to be shifted. Okay, and you keep on doing this. You keep on shifting. I mean, for each of those things, it will sort of, slide down a little bit. And then at some point, this will be 1 and the rest will all be zeros. So then it suddenly becomes H. And that shifts down. Okay, so that's what this matrix looks like. So there are D2 such columns here, and these are D1 such columns. And this is what the matrix representation of TGH looks like. Okay, and this matrix has a name. So this is called the Sylvester Matrix. Of F, why do I keep saying F and G? I'm pretty sure I make this mistake later on in the notes. Okay, and it has it's a pretty, it's a very structured matrix somehow, which seems to capture the linear transformation that you want. And the resultant is just the determinant of this matrix. Okay, and this is the definition of what a resultant between two polynomials is. It's just you look at the Sylvester matrix and look at its determinant. Okay, and what do we know? We know that this is equal to 0 if and only if just GCD of G and H is non-trivial. Because determinant being equal to 0 is exactly going to tell you, is there anything in the kernel or not? Okay, and we just saw that this particular linear operation has things in its kernel, if and only if the GCD was not trivial. So somehow the resultant is some weird sort of number at this. Notice that right now G0s are all basically coefficients of the polynomials involved. So this matrix is just made up of a bunch of scalars. So eventually you get one number involving the coefficients of G and the coefficients of H. And that number is telling you whether or not the GCD of G and H is not real. Okay, it's a completely different way of figuring out whether there is a non-trivial GCD between two polynomials. Right? I hope. So this is what the resultant is. It's a super, super powerful thing. And here is the real kicker, which is that you can now generalize this over more variables. Okay, so here is the more general statement. Suppose now your polynomials were bivariates instead of univariates. Okay, but I'm going to pretend like these are univariate polynomials in X, but each of these G1, G2, whatever, they are actually polynomials involving Y's. Like I'm just look at all terms that involve X power D1, collect them all together, I put that in GD1. Look at all terms in X power D2, collect them all together, and put it in GD, whatever. So each of them are polynomials in the Y variables. Okay, similarly, I can do the same thing for the H's. And now you do the same thing, you just look at the resultant again, except now G0, G1, all of them are polynomials in the Y variables. Previously, they were all constants. Now all of these coefficients are polynomials in Y. Okay, and turns out that if you now look at the resultant of the pair of polynomials, which is now going to be a matrix that is made up of all the Y, whatever, these Y coefficients, and then you compute the determinant. So now this determinant is going to be a suitable polynomial in Y. Okay, and surprisingly, that particular polynomial is equal to 0 if and only if G and H have a GCD, non-trivial GCD. But you need to be careful about what non-trivial GCD means. We are living in the world where Y is a constant. So we want to know if there is a GCD that involves the X variables somehow. Okay, so I mean, this is what I was trying to eventually get to, which is the fact that the resultant is a super powerful operation because it gives you a way of writing down one expression involving the coefficients that tell you whether or not there is a non-trivial GCD. It's not an algorithm in the traditional sense, but it's like something like a certificate that you can get about whether or not two polynomials share a GCD. Okay, it's a pretty powerful thing. And in fact, if you're really interested in the proof of this, you basically apply the previous proof that we did. But notice that the previous proof involved working with a field. Like all of these G0s, G1s, etc. needed to come from a field. So what you do is like you just pretend to work over this thing and then use Gauss Lemma and get done. Okay, that's like I'm hand waving a lot for what the proof is. But at this point, I only want to tell you the main lemma involving resultants. And this is what makes resultants powerful. Okay. So at this point, let me make one extra observation before we see an algorithm for this class. Okay, the first observation is just the following, which is if G and H are polynomials of, let's say, degree D. Okay, if I look at a resultant with respect to X of G and H, that involves the determinant of a matrix that is made up of entries which are all polynomials in Y. Right, so therefore the resultant is certainly some polynomial in Y. It's some ugly polynomial. I don't know exactly what the polynomial is, but let's give a stupid bound on how large is this polynomial. Okay, notice each of them, I mean, the largest possible degree they can have is D because it's one of the coefficients of the two polynomials that was involved. And this matrix, okay, at best, it's a 2D cross 2D sort of matrix. So a stupid bound you can put on the degree of the resultant is just 2D times D, which is 2D squared. Okay. So this 2D squared will start showing up a lot. I mean, whenever you see a 2D squared in a problem, you will know that some resultant is involved. Okay. Okay. So why did we do all the resultants? And the reason we did all these resultants is because I eventually now want to present to you the algorithm for computing a GCD of two bivariate polynomials. And it's one of these, I don't know, it's a typical computer science way of doing things, in the sense that we are literally going to just reduce the bivariate GCD computation to the univariate GCD computation. We're just going to tell ourselves, look, I only know how to do univariate GCD. I don't mind doing as many univariate GCDs as required. I want to somehow do enough in order to be able to recover the bivariate GCD. Okay, and this is what is going to happen. And the resultant is going to play a key role to figuring out how many such univariate GCDs do we need to do. So let me just write down, I'll just tell you the full algorithm and we will see why this is true. I mean, why this works. Okay, so here is the input. Your input is like two polynomials, which I'm going to assume are both monic in X. Okay, if they are monic in X, notice that there can't be any there can't be any factor which is purely in Y. Right? Because the highest degree term must involve X. You can't have something which is a pure function of Y. It's just convenient to get rid of all of those other nonsense. Okay, so here is what I'm going to do. I'm going to choose a whole bunch of field elements. Okay, distinct field elements, and look at the univariate versions of this by substituting Y equal to AI. Now I have two univariate polynomials, f of x comma AI and g of x comma AI. Now I know how to compute GCD of those two because they are univariate polynomials. So let's just compute the polynomial hi of x, which is a GCD of, you know, AI and whatever. So morally speaking, what do I want hi of x to be equal to b? So suppose, okay, h star of x comma y is the true GCD. Suppose this was the correct GCD. I am really hoping that hi of x is basically h star of x comma ai. Okay, that's what I'm hoping happens. But this may not be the case. But so I'm going to do, so this is the part that's a little weird. Okay, which is what I'm going to do is for each of these hi of x's, I will try and figure out what are their degrees. I mean, ideally speaking, if all of them are equal to h star of x comma ai, they must all be of the same degree. Right? Because the GCD is monic, and whether I substitute something or not, the highest degree term is going to stay what it is. That degree is not going to change. But maybe some of them weirdly have slightly different degrees. Okay, so what we'll do is among all the HIs that we got in the process, let's look at the HIs that have the smallest degree and collect all HIs that have this minimum degree. I mean, in a few minutes, you will see why this is necessary. Okay. And now what I do is I basically say I am looking for h star of x comma y. Whatever this h star of x comma y is supposed to have the property that h of x comma ai is equal to hi. And you compute such a polynomial using interpolation. Okay, and this in some sense is the overall algorithm. I mean, it feels like morally it should work. I mean, it's like saying, I only know how to compute univariate GCDs. I'm hoping that each of the things I computed was actually h star of x comma ai, where h star was the true GCD. So once I compute all of these univariate polynomials, I'm going to interpolate and figure out the bivariate polynomial. And I'm hoping that this algorithm will work. I haven't specified what t is. This t will depend on our correctness proof. So is the algorithm clear? I mean, this is a slightly weird algorithm. It's a weird way of reducing GCD to one variable less. But yeah, but this is going to be super convenient because once we do this, we will see exactly how you do trivariate GCD. You will do exactly the same thing. You will reduce to bivariate, do that, and then interpolate out. Okay, so let's see the correctness. I basically want to understand the following question. What can I say about the true GCD of f comma g versus the GCD of f of x comma ai and g of x comma ai? What can happen? So can I say that one of them must always be greater than the other or something of that sort? So let's just, so suppose f was equal to the true GCD h star times some u of x comma y, and g was equal to the true GCD h star times some v of x comma y. So now what are these? This is going to be h star into some u of x comma ai, and this guy is equal to h star times v of x comma ai. So what can happen is that certainly if h star is a GCD here, you will at least get h star of x comma ai on the right hand side. The problem is, annoyingly, these two could now have some extra factors. Like it may have been the case that u of x comma y and v of x comma y had no factors. But once I substitute y equal to ai, maybe u of x comma ai and v of x comma ai now share some factors. I mean, think of a situation where this guy is equal to something like x squared plus y, and this guy is equal to x, x squared plus 2y. I mean, x squared plus y and x squared plus 2y don't have any factors. But once I put y equal to 0, I get x squared and x squared. So suddenly they start sharing a lot of factors. Okay. So we might be in a weird situation where the AIs that we choose are such that originally they didn't have any GCD. That u of x comma y and v of x comma y didn't have any GCD. But substituting y equal to ai suddenly makes them have some GCDs. I want to call them the bad substitutions and I want to get rid of them. So that's basically what we are doing here. We are basically saying if the degree suddenly changes, if suddenly your GCD appears to have larger degree than what you're supposed to have, throw all of those away. Just focus on the smallest degree that you have obtained for the GCD and let's focus on this. Okay, so hopefully that gives you some insight as to why we are doing this particular process. It's just that you could have some extra GCDs because the AI that you chose was a bad AI. Okay, so I really want the entire algorithm really boils down to, okay, some of these AIs could be bad, but are there sufficiently many good AIs for me to interpolate? And this is really where the resultant comes into the picture, because it lets you quantify when this can happen. When can it be the case that u of x comma y and v of x comma y didn't have a GCD, but suddenly when I make the substitution, it does have a GCD? Can I exactly tell you what AIs are bad and what AIs are good? That's where the resultant comes. Okay, so here's what I want to do. I want to say h star is the true GCD, and I want to get a sense of when are we sure that hi of x is actually equal to h star of x comma a. Okay, so this is the, so this want to make sure that u of x comma ai and v of x comma ai don't have any GCD. Okay, so let's ask, when can it be that GCD of u comma v, this is equal to 1, but GCD of u comma, u of x comma ai and v of x comma ai, this is not equal to 1. Okay, what does this mean? When will this GCD be equal to 1? So this happens if and only if the resultant of G and H, or sorry, of U and B is not equal to 0. Okay. I mean, GCD not being 1 is the same thing as saying the resultant is non-zero. What does this mean? It means the resultant with respect to X of U of X comma AI and V of X comma AI, this is equal to 0. What's the connection between this and this? What really has happened? What is the only change that has happened? So this was a polynomial over the Y variables. Right? That polynomial ended up being substituted at Y equal to AI in the right hand side. Because literally every entry in the matrix is going to just have, instead of whatever G naught or something, it's going to have G naught of AI, etc., etc. So what is happening is that this as a polynomial used to be non-zero. But when I substituted AI, the polynomial became 0. Okay. So now it tells you exactly what the bad AIs are. The bad AIs are those that happen to kill the non-zero polynomial, which was the original result. Okay. So how many roots can whatever res x of u comma v have? So this is at most 2d squared, because I know it's a polynomial of degree at most 2d squared. Okay, so this is a polynomial of degree at most 2d squared. So worst case, on 2d squared of my choices of these AIs, I could have ended up making the resultant equal to 0, and then weird things are happening. I don't want to deal with them. Okay, so which means, therefore, the number of I such that h star of x comma y is equal to hi of x. Sorry, h star of x comma ai is equal to h of x is at least t minus 2d squared. 2d squared of these points could have been bad, but if you ignore those 2d squared points, then you know for a fact that you are indeed the correct, you're talking in terms of the true GCD. So that's what you do. You just need to make sure that this t is large enough. So t is bigger than or equal to 2d squared plus whatever needed for interpolation. So usually people choose just 4d squared and just be done with it. Okay, so you need to eventually interpolate all of these things. So for that, you will need sufficiently many evaluations so that you can interpolate. So you just make sure that there are whatever, you have 2d squared of error terms plus whatever you need for interpolation. And that completes the proof of the bivariate factorization. And this is exactly the same proof for trivariate factorization, degree 4, like 4-variate factorization, etc. Because it's really just a reduction to one less variables. You are reducing to one less variables, using the bivariate sort of the GCD computation at that level, collecting all the answers that you get at that level, and putting them together to get your true GCD. And you just need to make sure what AIs are good and what AIs are bad. And you don't have a good handle of which of these AIs suddenly introduce some spurious factors. But that's where your resultant is going to come to your rescue and basically say that I will tell you exactly which AIs are bad. So because the resultant has some small degree, at most some small number of these AIs are going to be bad. And you can use your degree as a check to just make sure that you're choosing only those that have the smallest degree. Anything that give you additional spurious factors, you throw them away. You just don't consider them. Okay, and that's the GCD algorithm. Great. So this is it's like a lot to sort of digest. And the resultant itself is a very powerful tool. I mean, and unless you see it a lot, I mean, it's hard to get a good grasp of how powerful the resultant is. And hopefully in the next lecture, we will see more applications of the resultant. So this basically at least comes up with the baby version, which is usually the first step you do in any polynomial factorization thing, which is to get rid of all the repeated factors, etc. And you can therefore do something similar to what we had done last time, which is the first thing is to somehow make sure that things are square free by taking GCDs with derivatives, etc. And these are all things we will see in the next class. I mean, I'm already going a little past time. Okay, so yeah, so let me just maybe take a moment to just recap what we have seen today. I mean, there are two fairly big blocks of some concepts that you have learned, and it takes a while to digest. So the first thing that we saw was the notion of Gauss's lemma, which is to basically artificially work with a univariate polynomial, which is by just mentally telling ourselves that we are allowed to have denominators whenever necessary, and we will deal with them as we deal with fractions. We'll just keep track of the denominator and numerator and deal with them. And Gauss's lemma tells you that this does not change your reducibility. Anything that used to be factor will continue to stay as factors. So you don't need to worry about this. This is a legitimate change that you can do if you need to. That was one. And the second most important thing is the notion of what is a resultant. A resultant is a way of capturing the following linear map, which is you just take two polynomials a and b, where a's degree is smaller than degree of h and b's degree is smaller than degree of g. And you just take a pair of polynomials a and b and return the polynomial ag plus bh. And the first observation is that this linear map has a non-trivial kernel if and only if the GCD was not there. Okay, and once you have a linear map somehow where the kernel is encoding information about whether GCD is non-trivial or not, you can immediately start looking at the determinant of this, the matrix that corresponds to this linear map. And that determinant is what the resultant is. So if g and h are polynomials in a certain number of variables, and you're looking at the resultant with respect to x, then the resultant is the polynomials on all variables besides x. So if the polynomial was just a univariate polynomial, then the resultant is a number because all of them are field constants. But on the other hand, if your polynomial is a bivariate polynomial and you're looking at the resultant with respect to x, then every entry here is a polynomial in just the y variables. And therefore, the resultant is also going to be a polynomial in the y variables. And you also know that if g and h don't have too large degree, then the resultant also does not have too large degree. And you can use this to come up with a GCD algorithm for bivariate polynomials. Okay, so in the next class onwards, it's okay if you don't completely internalize the GCD algorithm. Just take it for granted at this point that there is a way of doing bivariate GCD, which is a little, and in general, there is a way of doing k-variate GCD. And we will just use that and proceed with the rest of the bivariate factorization. So that's what we will do on Thursday. Okay, so let me stop here and sorry for going a little over time. So if there are any quick questions, we can take it. Otherwise, we'll just meet on Thursday.
Sir,
Yeah, go ahead, Shantanu.
sir, I have a query regarding the course, not about the lecture.
Sorry, by the way, so shall I just maybe end stream in that